Hello everyone, my name is Jan Richard. I'm from the Institute for Energy Efficient Buildings and Indoor Climate of the Technical University of Aachen in Germany. In this talk, I'd like to present our work on the optimization of modernization measures for non-residential buildings by using a genetic algorithm. Why is it important to identify modernization measures for non-residential buildings? As many other countries, Germany has set himself some climate protection goals that lead to an extensive change in the energy supply of buildings. The building stock does only grow slowly, and therefore existing buildings play a key role. Most of these buildings were built over 40 years ago and hence with low energy requirements. Modernization measures have long-lasting effects on energy and economical performance and thus need to be identified systematically. Non-residential buildings account for a significant share of the energy consumption and can therefore make a significant contribution to the climate protection goals. Main challenges during the planning of modernization measures for non-residential buildings are their heterogeneous usage and poor existing databases. Not only general statistics are missing, there is also a lack of time series that are needed for the analysis with simulation and optimization approaches. We determine some typical time series and use them for the demand calculation inside a RC model. The hourly demand is then used for the optimization of modernization measures with a genetic algorithm. Finally, we apply this method on a typical non-residential building. We aim on multi-zone demand calculation, the categorical consideration of building types, and a multicriteria Pareto optimization for the modernization measures. In practice, we see that static normative approaches often lead to inaccurate demand calculations. Dynamic, highly resolved building models may overcome this drawback. RC models are a promising approach where heat transfer is represented by electrical resistances and storage ability of, for example, the envelope by capacities. Our approach is based on a proven RC model for residential buildings that represents the energy balance of a building. We extend this model by zone-specific calculations of internal loads for non-residential buildings. These are based on presence and activity profiles in Swiss Standard 2024. For the later shown case study, we get these profiles for the electrical power of user appliances, which are one part of the internal loads beneath lighting and heat by people. Here, for example, in the laboratory zone, we see a typical working day with two peaks and one lower point that represents the lunch break in the main usage zone. The modernization of buildings underlies many different influences that can be put in mathematical equations and then be part of optimization models. Genetic algorithms are often used concerning building energy systems. The general procedure of a GI is shown here. In our case, the population includes possible sets of modernization measures. Part of these sets can be insulation measures for the envelope and the exchange of the supply system. At the disposal of the algorithm are boilers, combined heat and power, compression and absorption chillers, different solar technologies, thermal storages, batteries, and many more. These are all individually sized for the building and can be combined in many ways. All sets of measures are evaluated by their annualized costs and by yearly emitted emissions. The algorithm then selects the well-performing sets and with crossover and mutation combines them with each other and also with new sets of measures. This procedure is repeated until the optimum is found. The presented method is applied on a laboratory and office building in Berlin. Here we see the heat and cold demand with simultaneous heating and cooling over the whole year due to server rooms and high internal loads of the laboratory zone. In the shown Pareto frontier, we see the two objective functions on the axis, and each of the points represents an optimal set of modernization measures. The emission reduction potential compared to the existing energy system is about 28%. In the near of the economic optimum, we see CHP and compression chillers in different sizes covering the demand. The compromise solutions include mainly pellet boilers and compression chillers due to the CO2 reduction potential of wood. More ecological solutions use pellet boilers and absorption chillers fed by district heating because of its low CO2 factor. In these solutions, also insulation and window exchange are realized. PV with a battery is part of nearly every solution of the here shown Pareto frontier. Summarizing our work done so far, we see that the demand seems to be modeled in a good manner, and a further validation is one of our next steps. The GA model also performs well and reveals high emission reduction potentials. In the future, we will examine the influence of the boundary conditions. Concerning the modernization measures for non-residential building, we see wooden-based technologies seem to offer high emission reduction potential, but their sustainable availability shall be kept in mind. Furthermore, we see strong dependencies of the energy system on the ratio of heat to cold peak load. One next step here is the adding of further technologies. Thank you all for listening to my presentation. I'd like to thank the German Federal Ministry for Economic Affairs and Energy for the promotion of our work. Also thanks to the organizers and reviewers of PLEA who made this presentation and the paper possible. And finally, thanks to my co-authors for the support during the paper preparation.